Hey y'all. Okay, so trying to get this to go away. What we're going to do today is 11.1, which is empirical and theoretical probabilities. So empirical and theoretical probabilities. Unsure why it's so hard for me to spell that word, but it is sometimes. Okay, so we have a few things that we need to define first. Whenever we talk about an experiment is a controlled operation that yields I before E, right? So just started to try to spell yields wrong. Oh, I've got white out in here somewhere. There we go. Okay. So an experiment is a controlled operation that yields a set of results. And then more specifically, kind of about these results that we're talking about, we call them outcomes. So our outcomes, they are the possible results of an experiment. And then this word right here, event, we hear it quite often, like over and over and over and over and over again, especially in this section. An event is a sub-collection of outcomes. So we have a sub-collection of outcomes, which we call our event. The outcomes are the possible results of an experiment, and experiments are controlled operations that result in results. Sounds kind of weird to say result in results, but that is what it does. Okay, so the first type of probability that we're going to talk about is empirical probability. If I get comfortable. So empirical probability . So empirical probability is determined by the relative frequency of an event. If you see the word frequency, that's kind of like your key word there, relative frequency, either of them, that you're dealing with empirical probability. Relative frequency just meaning like how often does something occur, like the number of times that it happens. Okay, and there's like this little formula that we use whenever we are calculating our empirical probability. So with probability, what we see a lot is a capital P, and then open your parentheses, do a capital E, and then close. So this is read like P of E, or probability of an event. So if it is an empirical probability that we're calculating, the numerator is made up of the number of times event occurs, so the frequency of that event, and then our denominator is the total number of times experiment performed. Okay, so empirical probability, how often does it occur over how many experiments were performed? How many experiments? How many times the experiment was performed? Okay, so we're gonna go ahead and we're gonna do an example. The math, honestly, in 11.1 is very simple, but the problems themselves could get very wordy. And so I'm gonna kind of show you the data that you need, the information that's important to answer all the problems. They could be confusing. Sometimes it's confusing only because it's simple. Like really. 11.1, we do this. 11.4, I think we do like tree diagrams, which is very simple. 12.2, 3 and 4 is like a mean, median, and mode. And then that's it. We're gonna do exam 4 and then we'll do the final. So you'll notice like kind of wordy for this first section, but the math is like really easy for the rest of the semester, okay? Okay, I have a thinner black. Let me switch. Okay, so a blood pressure test is completed with 500 adults. Comma, each taking new medicine. Ran out of room, just gonna say med. The homework, obviously, as usual, is way wordier than the example we do today, but I am just trying to kind of simplify it just a little bit, okay? 379 reported reduced pressure. $62 unchanged. And 59 increased. Determined the probability of the following. Round 3 decimal places. Okay, so it's an ABC part. I'm just gonna kind of try to smush it on here. Again, the homework's always more wordy. For part A, it'll actually say, what is the empirical probability of selecting a person and their blood pressure has been reduced? It'll be like a whole sentence, okay? But I'm literally just gonna write the word reduced, okay? What we're doing is finding the empirical probability that, the next person that is selected is, has experienced, I don't know why I like stuttered there, has experienced reduced pressure. So I'm actually trying to figure out how I'm going to fit all this and smush it. So what we do, it's the probability of this event occurring. Anytime you do probability, I always start with my fraction bar. And then if we look right up here, when it's empirical probability, our numerator is the number of times the event occurs. Here, the event that we're talking about is their blood pressure has been reduced after taking this medicine. And so how many actually reported that their blood pressure was reduced? It was 379. And then the denominator is the total number of times that the experiment was performed. That's the 500. I actually left so many calculators at home on accident this morning. This is the same calculator y'all use in class, but it's the pro version. It's just one of my personal ones. So I'll go ahead and do the problems on it. It just looks slightly different than the one we use in class. So if you do the N over D button and you do 379 divided by 500, it gives it to me as a fraction. It actually can't be reduced. Them telling me to round 3 decimal places means they want it as a decimal. And so the answer that I get is that the probability is equal to 0.758. Like that's what you enter onto my math lab. Okay, and then it's like, find the empirical probability that the next person that is selected experiences an unchanged in their blood. I mean, it's like, there's all these sentences, right? But we're just gonna go ahead and say unchanged. That's what we're doing. We're finding the probability now of it being unchanged. I'm gonna do an arrow just so I don't have to smush too much here. Probability of an event. Well, if I look, I know that 500 is the number of times the experiment is being performed, and then unchanged is 62. And then if I put this into my calculator, if you notice, whenever I did the N over D button, it gave it to me as a fraction. So if you just do 62 divided by 500 in that manner, without the N over D, it gives it to you as a decimal. And so that's what I want. The answer would be 0.124. That's the probability. Okay, and then lastly, what's the probability of the blood pressure being increased? So the probability of this event occurring is the number of times the event occurs over the number of times the experiment is performed. There were 59 participants who experienced increased blood pressure. And if you put this into your calculator, just kidding, 59 divided by, there we go, we get 0.118. Does that make sense? Okay. Literally, that's the math. Pretty much in this whole section. It's just reading the question, knowing what it's wanting, understanding, and I'm fixing to show you the other probability, but understanding the difference between empirical and theoretical. Oh, you know, come grab one of these. One of each. This one's our schedule for the rest of the semester. So you'll see there's only a few things left, and then this we're going to look at kind of towards the end of the lesson plan. But definitely have kind of gotten over a hump as far as the material being difficult. Now it's just like easy breezy, lemon squeezy. Okay, so what do we have now? Now let's go ahead and define theoretical probability. Okay. Theoretical theoretical probability is determined through a study of possible outcomes. Okay, so if each outcome has the same chance of occurring, so like they have equal chances, right? With a frequency way more experienced, reduced blood pressure, and like the number of each of those three different events occurring, they were all different, right? Whenever we talk about theoretical probability, these outcomes all have like an equal chance of occurring, okay? So the probability, we still use the same like notation. It's still P of E. It's still the probability of an event. It's what goes in your numerator and what goes in your denominator that differentiates the two. In our numerator, for theoretical probability, we have the number of outcomes favorable to E Whenever I say favorable, I've always told my students this. What are they talking about? Or let's say asking. What are they asking? It's the probability of blank, right? Whatever that blank is, that's what they're asking us about. It's like that's what we pay attention to. And then it's over total number of possible outcomes. So it's favorable over total, okay? So total number of possible outcomes. Okay, now let's do an example. Someone is blowing me up. Okay. Example. So, a fair six-sided die is rolled. Determine the probability of rolling, and we're going to do dot, 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 because we're actually going to do an A, B, C, D, E part. Never fun to do this, but I'm going to draw. So fair just means that the die that you're rolling is not weighted. And when a die is not weighted, quite literally means that nothing has a greater chance of being rolled. Everything has an equal chance of being rolled. And so because of that, it's theoretical probability and not empirical. Empirical, everything had different frequencies. Everything occurred at, different number of times. Theoretical, everything has the same possibility of being an outcome. Try to figure out what color I want to go here. Okay. And then I added six-sided. I don't think on the homework it tells you six-sided, but usually it's always six-sided unless they tell you anything different. And so the different rolls that you could roll would be a 1, a 2, 3, 4, 5, or 6. For part A, it's asking me to determine the probability of rolling a 2. So what you do is probability of 2. Whenever we do probability, I always start with my fraction bar. Excuse me. And if it's theoretical probability, it's favorable over total. What are they talking about, or what are they asking over total? If it is a six-sided die, the total number of possible outcomes for my denominator would be 6. Okay? And then how many times does this event occur of rolling a 2? It only occurs one time. So you do 1. And then that is actually in reduced form, and that is your answer. Okay? For B. So, determine the probability of rolling an even number. So if I look at the probability of rolling an even number, even is 2, 4, and 6. So there's 1, 2, 3 favorable outcomes in this event over 6 total outcomes, and that reduces to 1/2. But just, free advice. Even and odd, it's always half. No matter if you have 10, which we're going to see, we have like 10 different outcomes. 5 would be even, 5 would be odd. Here we have 6, 3 are even, 3 are odd. Okay. Okay, so for C, we have what's the probability of rolling a number greater than 2. So a probability of rolling a number that's greater than 2. If you notice my denominator, that hasn't changed, right? Each time I figure out a new probability with this 6-sided die, the total number of outcomes has always been 6. It's the numerator that changes based off of like what they're asking me. So here, numbers greater than 2. Okay, it didn't say or equal to. So I don't start with 1 or 2, right? This is less than 2, and this is 2. And so it's not greater than 2, but numbers greater than 2, there's 1, 2, 3, 4 numbers greater than 2, and this would reduce to 2/3, and that is your answer. And some people might actually be able to see that if there's 6 things, you could separate it into groups of 3, right? This is a group, groups of 3. Groups of 2, there's 3 groups of 2, right? And so if I end up getting 4, it actually ends up being 1, 2 groups of 3. It's just basically just got reduced. Let's do D. This one's important. Determine the probability of rolling a 7. Well, okay. Probability of a 7. Probability, I do my fraction. I know I'm doing theoretical because it's a die. And I know that the total number of outcomes is 6. And then I look at the number of outcomes favorable to this event. This event is rolling a 7. The number of outcomes favorable or like this happening would be 0, right? Because 7 does not exist. And then 0 divided by anything is just 0. So this is an impossible outcome. So there's like an impossibility here, right? It can't happen. And then also important pertaining to probability, for E, determine the probability of rolling a number less than 7. I know that the total number of possible outcomes is 6. My numerator should be the number of outcomes favorable to E, or what are they talking about? They're talking about numbers that are less than 7. And I noticed that 1, 2, 3, 4, 5, 6, every single number, each side of this die is a favorable outcome to this event. So all 6 outcomes would be my numerator. 6 divided by 6 is 1. So this is like for certain, like it must happen. That makes sense? Okay, now I'm going to kind of just write these down again, like what it means to get a probability of 0, what it means to get a probability of 1, and a few other like little important notes about probability. Like these would be the things that I would have written on my note card for exam 4. Okay, so I just call them important probability notes. They also are kind of like the definitions that we do on the first page, where like in the homework, like they'll ask you questions about like this little chunk right here, okay? So important probability notes. So like I said, if you have the probability of an event occurring equaling 0, what this means is it cannot occur. Probability of rolling a 7 with a 6-sided fair 6-sided die, it sounded weird, is 0. It cannot occur. You literally cannot roll a 7 if you have a 6-sided die. Okay, and the probability of an event occurring equaling 1, this right here means it must happen. That's why the probability with a 6-sided die of rolling a number less than 7 6 over 6 gave us a 1, means no matter what, it must happen. It's like for certain, it's gonna happen. Okay? And then this right here, if we write 0 is less than or equal to the probability of an event occurring is less than or equal to 1, all this is saying the probability of any event is not only less than 1 or greater than 0, meaning it falls right in between there. It also can include it. So you might see the word like inclusive. This is saying that the probability of an event cannot be negative. Or an improper fraction. Obviously, it cannot be negative because that would mean that it is less than 0. And this right here tells me that the probability of an event lies between 0 and 1, so it can't be less than. And then the probability of an event occurring cannot be an improper fraction because all improper fractions are greater than 1. Okay, so that basically just kind of like takes you outside of these boundaries right here, okay? They don't really do a ton with this. I mean, it is something that's very important, but this right here, the sum of all probabilities. Why did I say that? Erase that. You got a pencil, sorry. I looked up and saw the letter P and wrote probabilities, but that is not correct. Okay, the sum of all possible outcomes. Possible outcomes. The sum of all possible outcomes is 1. Okay, so I'm going to give you these two little equations. They are the exact same. The second one's a derivative of the first, and the second one's the one you use more often. But the sum, right, so I'm adding things together, of the possible outcomes is 1, right? Is means equal. So this is what it looks like. If you have the probability of an event, this is saying the probability of an event occurring, right? It actually happens. And you add to it the probability of the event not occurring. What you end up getting is 1. So the probability of it happening and it not happening should always sum to 1. That's what that sentence means. Now, what you'll use more on the homework is this variation of this equation. What they do is, let's say we wanted to solve for an event not happening. I want to solve for this right here. Well, I would subtract this from the left-hand side and subtract P of E from the right-hand side, and you would get this. So this is a derivative of this, right? I just subtracted P of E over here, and then I subtract P of E over here, and you end up getting this. This is the one that you would use on your homework, and this is how to find probability of an event not occurring or does not occur. Okay, so how to find the probability of event not occurring. I don't know why all day today occurring has looked like it's been spelled wrong, but I am going to be okay with it because it is fine. I feel like there's 2 R's. I've already been told there's not, and I still think there is. Okay, let's do an example. Actually, we have 3 examples. Literally, couldn't be easier examples, okay? Example 1. The first one's a little bit wordier, and then I kind of simplified a little bit, okay? So, the probability of an event occurring is 0.49. find the probability the event does not occur. And then right here, how to find the probability an event does not occur. And there's really no reason to write anything other than 1 minus the probability of it occurring. All you've got to do is 1 minus P of E. P of E is 0.49. Now, if you get your calculator and you do 1 minus 0.49 or 0.49, what you get is 0.51. This is the probability that the event does not occur given the probability of the event occurring by subtracting it from 1. Because I know that the sum of these equals 1, I can do this little math right here, and that's your answer. Okay? So for the second example, if we have the probability of an event occurring being 0.8, find probability of it not occurring. 1 minus 0.8 is what? 0.2. And then for our third example, the probability of an event occurring is 0.36. Find the probability the event does not occur. So still right here, use this formula with the arrow that says how to calculate this. If you take your 1 and you subtract the 0.36 and you put that in your calculator, you should get 0.64. Make sense? Okay. I was saying, and I'll say it again, the math in this section is way easier than it has been. Sometimes it's just reading the question and understanding what it's wanting. And definitely don't get confused by these. If these don't make sense, just let me know. Okay? Okay. So, now, I have 1, 2, 3, I think I have 5, where is it? Right here. I think I have 5 homework examples, and that was it. Let me put this one, this was an extra one for this class. And I'm gonna put it right here. Okay, homework examples. I think there might be 6 examples. It's a handful, okay? Okay. A phone has the digits 0 through 9. If a key is randomly selected, what is the probability of selecting? We're going to do ... because we have A, B, C, D parts. There was one thing I wanted to point out though, just make sure, because I mean this is similar wording that I would put on the test and you will see it on the homework. If you actually list out 0, 1, 2, 3, 4, what's the total? What's the sum of those digits? How many are there? A lot of people think 9 because it ends right here in 9. But if you go 0, 1, 2, then you count it all the way, you actually get 10. There's 10 digits. Okay. And actually we'll like list them in these little ABC parts, or BCD parts. But if you do accidentally think this ends in 9, that means there's 9 digits, and you use 9 as your total in your denominator, everything's messed up, okay? So for part A, what we're going to do is compute the probability of selecting a 9. Now this one didn't tell me whether or not it was empirical probability or theoretical probability. Empirical, everything occurs a different number of times. Theoretical, everything is the same or has like an equal chance of being selected. If you think, well, just think right here, y'all. This is like a phone, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 digits, right? And if you look, 7 has a frequency or occurs once. 8 occurs once. 9 occurs once. Everything occurs the same amount of times, so everything has the same equal opportunity of being selected. It would be different if it was like, there's 3 7s, there's 5 9s. You know what I mean? That would be a frequency, and that's when we would do the empirical. And the problem itself would have a whole bunch of different numbers listed, and you'd have to use those in your math. Here, it just wants to know what the probability is of selecting a 9. So I know it's theoretical. Everything has the same equal chance. I'm going to solve the probability of a 9. Theoretical is like, what are they talking about, or the favorable over the total. There's 10 total numbers or digits or keys, whatever they end up calling it, okay? And then how many times, what is the favorable outcome? How many times can I select 9? 1 time, because there's only 1 9. And then if you have 1 in your numerator, it's already reduced as much as it can be. 1/10, that's your answer. If it tells you round to so many decimal places, obviously they don't want a fraction as an answer. Okay, so just kind of would use that as like my hint of how do I keep my answer. Okay, what about B? Okay, so if a key is selected at random, what's the probability of selecting an even number? So the probability of an even number, theoretical, favorable over total. I'm still dealing with the exact same 10 keys, right? Brand new little experiment that I'm doing, or a little trial kind of. It's a new part of the question. So I said earlier, whenever we were talking about the dice, even and odd, there's always how many of each? Yeah, because there's always half, right? Here my total is 10. So that means that there's an even number of odds, and there's an even, I'm sorry, why did I say even? There is half of the digits that are even and half of the digits that are odd. And I could list them like this though, y'all. 1, 2, 3, 4, 5, 6, 7, 8, 9. If we're doing even, what they do is they actually count 0 as even. It should tell you that, but if it's something that it does not tell you, just understand that I told you even and odd, there's always half. Half even, half odd. So, like Mario said, there's 5 even numbers, but 5 divided by 10 is 1/2. Okay, there's always half even, half odds. Okay. And let's do C. So now, if a key is randomly selected, what is the probability of selecting a number greater than or equal to 6? I want to find the probability of a number that is greater than or equal to 6. I'm going to go and list them here. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And I just go through there, and I'm like, 0 is not equal to or greater than 6. Neither is 1, neither is 2, 3, 4, 5. Okay, hold on. A number greater than or equal to 6. So that's going to be my 6, my 7, my 8, and my 9. How many favorable, times do I have? Would be 4. Total number of outcomes is 10. 4 are the favorable ones that are greater than or equal to 6. And then, I didn't break this down. Well, it would just be 2/5, right? If you reduce this, you would get 2 over 5. I don't know why I wanted to box that one in. I didn't do the other ones. Okay, does that make sense? Okay. And then we have D. Right, so I'm looking at this phone. It has all these digits, and it's like, if a key is just selected at random, what's the probability of selecting a number less than 3? It's like, okay, so what's the probability of selecting a number that is less than 3? And if you list them, let me list and then just kind of stop instead of listing all of them and marking them out. If I start at 0, I know 0 is less than 3, so that's good. 1, less than 3, good. 2, less than 3. 3 is equal to 3. It is not less than 3, so I'm done here, right? There is only 1, 2, 3 favorable outcomes out of 10 outcomes. 3 is prime. It couldn't be reduced any further than that. Does that make sense? Okay. The greater than, less than, or equal to's, the word and or, stuff like that in this kind of section and exam would be what to pay attention to, because they, could kind of change the work that you do dramatically. If you don't understand 3 is not less than 3, you're going to have 4/10 and you're going to answer 2/5 and it's not going to be right. Okay? Okay. Let's do this one. I have an Herbalife tea and a Monster, and I am tired, or whatever. Oh, Red Bull. Still don't have wings. Let's say you're sitting at Walmart at the McDonald's being ornery. So it's like watching people walk in, right? So 60 people. It's actually fun to do sometimes, y'all. 60 people have walked into Walmart. Okay, so 17 had a yellow shirt. 13 black. 25 brown. And 5 red. So on the homework, little bit wordier, right? It'll be like 17 had a yellow shirt, 13 had a black shirt, it'll say all the words. And then whenever they do like the part A, this is where it'll say determine the probability, or it'll say determine the empirical probability that the next person that walks. It's just a super long sentence. So I kind of pulled that similar chunk and put it here, and then we simplify our like A, B, and C, D parts, okay? So what we're gonna do, it actually tells you which it shouldn't have to, but it does. It tells you to determine if I'm determining the probability in this problem, and I notice that each different possible outcome has a different chance of occurring, that's what makes it empirical. Okay, theoretical, it's like coins, right? It's rolling a die, like everything has the same equal chance. Empirical, everything has different numbers in front of it. Okay, the homework will actually tell you. This was that first page, right? Determine the empirical probability that the next person has a ... We have A, B, C, D parts. A is going to be a yellow shirt. You can probably follow my trend here. B is going to be a black shirt. C, a brown shirt. D, a red shirt. Again, they tell you use the empirical probability. And it's, y'all, it's still the same-ish. It was what the number of times this event occurs over the number of times the experiment's performed. But it's still like, what are they talking about over total, right? So the probability of a yellow shirt would be the number of times this occurs. How many times did the yellow shirt occur? 17. Over the number of times the experiment's performed, to 60. Okay? So if you do 17 over 60, you get 17 over 60. On this homework problem, they wanted you to keep it as a fraction that's not reducible. 17's prime, that's your answer. Okay? So with dice, we noticed that we use the other probability. With this one, they almost seem very, very similar because they are. But here, I actually use the number, right, that goes with yellow. Yellow and yellow. And it was 17. And then now, what's the probability of a black shirt? Well, 13 black shirts. So probability of a black shirt, okay, it's the number of times that the event occurs over the number of times that the experiment is performed. That denominator doesn't change. Put it over 13. 13's prime, that would be your answer. It won't reduce any further than that, okay? I don't have any other colors. So, brown shirt, 25 brown shirts. Probability that the next person that walks into Walmart, the empirical probability, would be 25 over 60. If you put that in your calculator, it should reduce to 5/12. That's the number of times that a brown shirt occurred over the total number of people that have walked in, and I've been collecting data on the color of their t-shirt. Red shirt, 5 red. Probability of red. Total number of times, 60. That's under my 5. And that will actually reduce to 1/12. Does that make sense, y'all? Good. I have to stand up. Okay, let's do this third example. Again, the little bitty math here and there, as long as you know where to pull your numbers from, it's not hard. And it doesn't take as long to kind of study and understand. It could be just the sentences or just the problems. They can be wordy, okay? Like this one, for example. Okay, so third example. At a bookstore in SoCal, 64 people entering were randomly selected and asked their favorite type of book. Chose sci-fi. 16 YA. 10 nonfiction. And 26 chose something other than sci-fi. YA, which is young adult, or nonfiction. Y'all don't even have to answer it, but I'm going to ask it. Would this be theoretical or empirical? Empirical is everything has like a different relative frequency, right? A different number of times that it occurs. Theoretical is everything is equal. Here, I've got 12 sci-fis, 16 young adult novels, and 10 nonfiction with 26. Those are all completely different numbers, right? So this is going to be an empirical probability where, depending on what it's asking me, I'm going to take either 12, 16, 10, or 26 and put it over 64. And that's going to be my answer, okay? You just really got to pay attention. It's like, what is it asking me? Okay, so, and the problem did tell you empirical probability, but we're going to go and write, determine the empirical probability of the following. And then I just kind of did like dot, dot, dot. Sorry. I'm wondering if I can shorten it. Determine the empirical probability of the following. Say person favoring. And then that way I don't have to write person favors for like 3 different times or whatever. Okay, so A. So we're going to figure out the empirical probability, like the next person favors sci-fi. So what I'm figuring out is the probability that the next person favors sci-fi. With empirical probability, it is the number of times that that event occurs. So sci-fi, 12 is its relative frequency, and then it's the number of times the experiment's performed, which is just that upper total. If it's not given to you, you would just, I think, add everything up. 64, 20, 30, 42, 52, 64, yes. Just want to make sure. Okay, and if you put this in your calculator, you should get a reduced answer of 3/16. And because that's how I left it in here, I'm assuming that's how they wanted it on the homework, as a fraction. I prefer like decimals, not percents, but decimals. But a fraction and a decimal are the two different ways that they might ask it for you to answer. Okay, what about that the next person favors young adult books? Okay, this would be probability of YA. I know that the number of times this experiment performed is 64. That doesn't change, right? And then I noticed within this big, huge problem that they gave me the frequency of someone choosing young adult novels was 16. So if you put that in your calculator, what you get as a reduced answer is 1/4 or 1/4. Does that make sense? Okay. Okay. Let's do the probability that the next person favors nonfiction. And so what we would be doing was figuring out the probability of someone favoring nonfiction, total number of times experiment has been performed, and my denominator has not changed to 64. I noticed that within my problem, I have 10 that did select nonfiction, so that's what my numerator is. And then if you put this in your calculator, you do 10/64. I get 5/32 as my final answer. And then lastly, so we want to find or determine the empirical probability that the following person favors something other. Obviously on the homework it says something other than the, and it lists like all the words, right? But I have this right here. Chose something other than, right? And that was this number that went with it, was the 26. So, but if I do the probability that they chose other, right? Something other. I know 64 doesn't change, and I know 26 was the relative frequency of the customers who chose something other than sci-fi, young adult, or nonfiction. And if you put this into your calculator, your reduced fraction is 13/32. Does that make sense, y'all? Yeah? Okay, good. Okay, so everyone should have a piece of paper that is near me. One, like I said, is our agenda right here. And then this right here is what we're fixing to refer to right now. Okay. So, I have some notes written on mine. And I wanted to show y'all this because mine actually prints in color. And I wanted you to be able to see. A lot of people actually don't know about like a deck of cards, okay? So a deck of cards, a standard deck of cards, has 52 cards. There are no jokers. We have 4 different suits: clubs, spades, hearts, and diamonds, with your clubs and your spades being black and your hearts and your diamonds being red. So if you notice, half are red, and then the other half of the deck is black. The cards start with ace, which can be worth either 1 or 11. Each of the suits have all of these cards: ace, 2, 3, 4, all the way up to 10. And then You may hear these referred to as picture cards. I've always called them face cards. We have jacks, queens, and kings in all of the four suits, half of them being black, half of them being red. We don't need this right here. But if you wanted to add these things to here, just so it kind of makes sense, you totally can. So my aces can count for 1 and 11. The top half, so the first 2 rows, are our black cards. The last 2 rows are our red cards. Our face cards, the 10 queens and kings, they count for 10 points. Okay? And then, okay, it does say here, like, if you look at the columns, 4 aces, 4 2s, 4 3s, 4 4s, there are 4 of every single card, because there's 4 different suits, and each card belongs to each suit. Okay? And there are 13 cards in each suit, which is why there's 52 cards total. So, this is what we're going to use to answer the homework problems about a deck of cards, and what we're going to use right now, actually. You ready? So, let's do this. This is our 4th example. Okay, so one card is selected at random. Determine the probability that the card is dot dot. So before you even kind of answer questions, you do obviously need to know that it's like you have to figure out if it's empirical or theoretical. And if you think about a deck of cards, everything has an equal chance of being selected. There's not 10 black ace of spades and then 1 of everything else. You know what I mean? Everything has the exact same frequency. Everything exists one time, so everything's equal. Okay, so I know I'm going to do theoretical. For part A, determine the probability that the card is an 8. Now, a lot of students will make a very common mistake and think, well, I would put 1 over 52. But that's implying that there's only one 8 card, or one card with the number 8 on it, or however you want to word it, in this whole deck, but there's not. How many 8s are there? It's 4 8s. Okay, so I'm going to do the probability of an 8. Theoretical was what? Favorable over total. What are they talking about over total? What is the total number of cards? 52. So that's my denominator. And then how many times does 8 occur? 4 times. If you put into your calculator 4 divided by 52, you should get a reduced fraction of 1 over 13. And that ends up being your answer. And then this is just something that if it makes sense, or if you see it, use it when you can, but if it confuses anybody, that's not my intention. With cards, what you usually can do is just pay attention to one row. So, because everything's going to reduce, right? So if I look here, there's 1 8 out of 13 cards, right? So 1 out of 13. Okay, I start with the whole total deck, so 15 is my denominator, and there's 4 total 8s. But if you notice working down, you'll kind of see you really only have to work within one row. Just pick one and just look, oh, there's 1 8 out of 13 cards. And that's just because of the way fractions can reduce, okay? So let's see what the probability is that our card that we randomly select is a face card. the probability of a face card would be favorable over total. Total is going to be 52. Favorable is what are they talking about? They're talking about the probability of a face card. If you look at your little helper right here, and we see how many face cards we have. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So favorable is 12 over total, which is 52, and that reduces to 3 over 13. And I'll say it one more time, and then I won't say it again. Remember, I just said you can kind of just look at one row. How many face cards do we have? 3 out of that 13. Just that one row. But don't worry about it because it takes 1 second for that to reduce in your calculator. Don't confuse yourself for sure. Okay. Okay. For part C, let's do the probability that the card is worth 10 or 11. So a card's worth is based off of what you see. A 4 is worth 4. An 8 is worth 8. An ace right here is worth 1 or 11. So I need to include those in my count. 10s, those are worth 10. And then all of these face cards are also worth 10. So if I figure out what the probability is of selecting a card worth 10 or 11 points, my denominator does not change because that is still the total number, which is 52. And if I look here, I know I'm going to count these face cards, which there's 12. I know I'm going to count all of my 10s, so 13, 14, 15, 16. And then I also count my aces, which is 17, 18, 19, 20. Okay, so that's the favorable. Favorable meaning, what are they talking about? If I pick up a queen, did I satisfy this probability? And it's like, yes, I did, right? There's 20 cards that are favorable. And if you reduce 20 over 52 in your calculator, you get 5 out of 13. 1, 2, 3, 4, 5. Okay, let's do D. What is the probability that the card that you select is a 6 or a jack? So the probability of a 6 or a jack is going to be equal to favorable over total. How many 6s are there? 4, right? 4 of every one. So that's 4. And then how many jacks are there? There's 4. So if you do 4 and 4, you get 8, right? There's 4 6s, 1, 2, 3, 4. And then there's 4 jacks, 1, 2, 3, 4. These 4 and these 4 together make 8. And if you reduce that, the answer that you get is 2 over 13. Is this making sense though? Okay. Let's do E. What is the probability that the card I select is not a 10? Don't get me wrong, you can do it, but the ones when we had like 0.36, 0.49, and we figured out the probability of something not happening and we subtracted it from 1, I would just use that on those problems. Right here, I wouldn't really try to do it. I would just keep doing what we're doing. We're trying to figure out that the probability of our card that we select is not a 10. So if I look, ace is not a 10, 2 is not, 3 is not, 4 is not, 5 is not. Do you see how it's everything except for 10s, right? So if I count all of these up, it's going to be 48. There are 48 cards in this deck of cards that are not the number 10. And so my favorable over total is 52. There are 48 favorable draws that I could draw that are not 10s. And if you reduce this, you get 12 out of 13. Okay, this one could be tricky. Just follow along with me. Okay, so what's the probability that the card is greater than 5 and less than 8? So what I'm looking for is the probability that I have a card that is greater than 5 and less than 8. I don't think they ask you to recreate this, but if you see it, I just want it to make sense. Okay, I'm going to do the favorable over the total. Total does not change. It's still my 52 cards. The favorable is, what are they talking about? And I know that they don't want me to include 5, and they don't want me to include 8, because there's no half of an equal sign here. So I think about the numbers that are actually less than 5, greater than 5 and less than 8. I have the probability of selecting a 6, and there are 4 cards there, 4 6s. As well as the probability of selecting a 7, there are also 4 cards there, for a total of 8 cards that they're asking me about that are favorable, that are the total number of cards that fall within being greater than 5 and less than 8. So if I look, okay, this is greater than 5 and less than 8, and so is 7. 1, 2, 3, 4, 5, 6, 7, 8. Nothing else counts. And if you reduce that, what you get is 2 over 13. That's the one that could be tricky. If you do like view an example and you see this, I just want it to make sense. If one of them does say equal, then you actually include that column of, cards, whatever it is they're talking about. Okay. Let's do this 5th example. The word pencil is written down and folded up The letters are placed in a bowl. Determine the probability of. Determine the probability of, basically like selecting the n. Okay. So, really? Okay. I keep pausing because I'm thinking about the homework problem and which word they used, and I'm just trying to make sure that at least my wording is like as close as possible. I almost want to say, because none of these letters occur more than once, I just want to go ahead and jump straight to doing like theoretical probability, because everything has an equal chance of being selected. And so I know that it is like the number of times that, hold on, I don't want to say it wrong. Favorable over total, right? So total, I have 1, 2, 3, 4, 5, 6 different outcomes. And then favorable is only the n, and there's only one n. So I would get 1/6. I don't remember if it was keep as a fraction or if it was changed into a decimal, but if it says round, obviously it wants you to use it as a decimal. Okay. Let's do the 6th example. It's just like this one, but me thinking for a second about the word they use. Some things do have a greater frequency of being selected, and so I just want to give y'all like a good example of that. Okay. So it's almost like A-B parts. We could do that. Nope, 2 completely different problems. Problem 6. Okay. The name, we're going to use my name. The name Jennifer is written down and folded. Instead of saying and placed in a ball, we're just going to say determine the probability, okay? But same type of thing, right? The J is written on a piece of paper, and E is written, maybe even this could kind of show too, right? These are all individual things. A J is written and it's folded, an E is, it's folded, an N is folded, an N is folded, an I, like each individual letter is written down and it's folded. And it's placed on the table, it's placed in a bowl, whatever. We're going to determine the probability of selecting an E. So the probability of selecting an E, whenever I look, some letters occur with a different frequency. There's more of them. So it's not theoretical where everything's equal, right? There are things that are not equal. I do know that my denominator is going to be all of them. So 1, 2, 3, 4, 5, 6, 7, 8. And then if I'm doing probability of E, there's 2 of them. And so I would get 1/4 or a quarter. And then one more example, y'all. This one, I really am pausing because I remember answering it, like I just saw it and I was like, oh, it's this. And I got it right. And sometimes when I do that, that's not good because like, I don't really know. You know what I mean? I don't question how I got it right. And I want to make sure that I explain that one right. I think they use the word Virginia or like a state. Like y'all's might change. It could be Mississippi or Hawaii or Virginia. Okay. Last one. I don't have, because I'm kind of doing this on the fly right now, I don't have all of the words that they use in the problem, but I do want, it's like maybe a spinner, right? So you've got a circle and you hit a spinner and it's like, what's the probability it'll land on? That's kind of what it is, okay? And so we have a circle. One of them is very similar to this. For problem 8, draw another circle. I did a cross and then an X. So essentially I broke this into 8 pieces. For this number 7, you can just write the word purple if you want, but let's do these 2 pieces, purple, bottom left piece is black, top right piece is blue. Hopefully y'all can kind of see that. Let me go a little bit thicker on this bottom left piece. Okay, so we have black, we have purple, we have blue, and we have purple. And then we have, like, for our A, so what's the probability of purple? I don't know how to draw a spinner, so I'm not gonna draw it. But say it's like, oh hey, you have this game that you're playing or whatever, and you spin the spinner. What's the probability that you could land on purple? And so what I see here is that there are 2 shaded areas, or 2 purples out of the 4 total, and so I end up getting half. The probability of landing on black would be 1/4. Out of these 4 pieces, there's one of them that would mean you landed on black. Out of these 4 pieces, there was 2 that were purple, so this ends up being half. Okay. Now this one, y'all, I did like 1, 2, 4, 7, 5, 3, 4, 2. This obviously is a tad simpler. I think they use money. It's like $100, $150, $200, $200. Maybe you're at the circus and you're gonna win some money and you gotta spin it. So the probability of landing on a 2, the way you work this is you notice you have 1, 2, 3, 4, 5, 6, 7, 8. That's your denominator. And then the 2 occurs 2 times. And that actually reduces to 1/4. That would be your probability of landing on a 2. And then probability of landing on a 3, we still have 8 total, pieces of this pie or spinny contraption, and 3 only occurs 1 time. So we have 1/8 of a probability of landing on 3 out of all of those different outcomes. Does that make sense? Okay. I didn't actually do those, and in the last class I threw one up on the board really quick, and I was like, hopefully it kind of makes sense, but if not, there's like ask why, or no, I think it says like more help on the homework, and if you touch it, it then says like email my instructor, and you could just be like, hey, I'm very confused about any of the questions you're confused about. It sends me an email, I can open up that exact question, work it out, take a picture, send it back to you, okay? So, other than that, that is it. Let me go ahead and turn this off, y'all.